Okay, this is practice problem CRS.C20.2. This is the second time we're looking at this problem. The first time we took matrices and found their column space. And of course that's pretty easy because the column space in a matrix is just the span of the columns themselves. The row is a little bit different though, and that's what this iteration is. We want to look at the row space. So I want a set of vectors that represents the row space of A. Our first step is generally to transpose the matrix. So I want to find a transpose, and of course that's just going to be all of the rows as columns. 1, 2, 3, 1, 0, 1, 1, 2, 0, or 1, negative 1, 2, 3, and 1, 1, 2, negative 1. Okay, and then once we have the transpose, now we want the reduced row echelon form. So I want RF of the transpose. And then that's going to give me, in this case, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 1, negative 1, 0, 0. So it's a pretty clean reduced row echelon form. We end up with 3 pivot columns in row 1, row 2, and row 3, okay? Okay, well, now let's get back to our task, which was to find a spanning space for the row space of A, and what set of vectors would perform that. Well, because we've transposed it now, the columns of the transpose are the rows of the original. So now I can just use a column span. And so the brute force is all of them. So the first answer for Y could be all of the columns of A transpose. 1, 2, 3, 1, followed by 0, 1, 1, 2, followed by 1, negative 1, 2, 3, and finally followed by 1, 1, 2, negative 1. So that's kind of what we would call the brute force. It's all of the columns, which are all of the rows, so this certainly would be overkill. That is a spanning set that will certainly produce all of the linear combinations of all of the rows of A taken as column vectors. But we can probably do better than that. Because RF indicated that we had pivot columns in 1, 2, and 3, we can use the BCS. Those theorem BCS allows us to reduce the spanning set to just those columns that actually produced pivots. So I can go back and say, of the transpose, I can just use column 1, 2, and 3. So Y could also be written as just the first 3 columns. 1, 2, 3, 1, followed by 0, 1, 1, 2, followed by 1, negative 1, 2, 3. Because they produced pivot columns, this would be a more efficient set of vectors, and of course this would produce the same spanning set as above. With appropriate linear combinations, these would both produce all of the same spanning sets. And again, the BCS kind of proves that, okay? And then we can introduce sort of a new theorem, and that theorem is theorem BRS. And what it says is this: because this is the reduced row echelon form of the transpose, I can actually take the vertical columns as the horizontal rows. In other words, I can indicate that this horizontal row here can become a vertical column and indicate the same information as before. So Y could also equal 1, 0, 0, 1, followed by 0, 1, 0, negative 1, followed by 0, 0, 1, 0. And of course, this is a much easier spanning set. This would be easier to check solutions in. This would be easier to build linear combinations of because it's got so many zeros and ones in it. And just to prove to yourself that they're the same, you can go ahead and put both of these through reduced row echelon form, and what you're going to get is exactly the same reduced row echelon form, indicating that these two matrices are row equivalent. In other words, they produce the same spanning set, okay? So again, that's the BRS, the BCS, and brute force. So that's three different ways of finding the row space of a matrix.